So we have another example on the problem relating to the viscosity of your fluid. You have a Newtonian fluid having a specific gravity of 0.92 and a kinematic viscosity of 4 times 10 to the power of negative 4 meters per second. It flows past a fixed surface. You have to take note that the problem is also saying that due to no slip condition, the velocity at the fixed surface is 0. And that is referring to the plate that you are seeing in the bottom part because that is not moving. And the velocity profile near the surface is shown in the figure above. Determine the magnitude. So this is what you are asked in the problem. You are to determine the magnitude as well as the direction of the shearing stress developed. Okay, we're looking for the shearing stress that is being developed on the plate. And again, the plate that we are talking here is referring to the bottom plate. Express your answers in terms of u, in terms of these variables here, and also in meters per second and meters per second and meters respectively. So the first thing that we need to do, the same as what we will be or what we are used to do in dealing with problems, is to note of the specific quantities which are given in the problem. Now in this problem, it is very clear that among the given above is the specific gravity. So I'm gonna write there SG, and in this problem that is equal to 0.92. And you have to note again that whenever we solve for a specific gravity, that is just related to the density of the fluid F all over the density of our reference fluid, which in this case, or as the standard reference, is your water at 4 degrees Celsius. So this implies then that the density of your fluid, which is something that is not given directly, can be solved by taking 0.92 multiplied by the density of our water, which is pretty easy to remember. Okay, another given is this nu here, which is your kinematic viscosity. It's given in the problem, and if you remember from our discussion, kinematic viscosity, that is just the ratio of your uh, absolute viscosity mu all over the density of the fluid F. And since that is given in the problem, the problem is saying that that is 4 times 10 to the power of negative 4 meters per second. This implies then that we can actually take out an expression for your absolute viscosity mu to be equal to 4 times 10 to the negative 4 meters per second multiplied by the density of your fluid. Okay, so I'm just gonna highlight these things here because this will prove important later. That's your kinematic viscosity, and this one here is your specific gravity. Now, take note that what we are actually looking for in the problem is it's asking us to find for an expression of tau. You remember tau is the shearing stress. So as you can see here, you need to determine the magnitude and direction of the shearing stress developed. So we're looking for tau. Now I'm just gonna change color into blue, and recall that tau is basically just your mu, absolute viscosity, multiplied by the velocity gradient du over dy. Now you have to take note that the velocity gradient, the one that I am highlighting, is something that is not directly given in the problem. So what you're going to do is to solve for this first. Now how do you do that? Of course, we will show in this lecture or in this problem. However, I failed to say earlier that this is your expression of the ratio of your velocity u that were developed within your fluid, and your u, which is the velocity of the fluid on the topmost portion over there. So that is given by 3/2 y over sigma minus 1/2 of quantity y over sigma to the cube. So that's your u over u. Now to find for the shearing stress tau, we have to find for that du over dy. So from the expression above, we are going to use the relation that is being um written above. So I'm just gonna do it in maybe, I don't know, blue, just to be consistent. So you have to note that you need to find du over dy first, and it's given in the problem that u, I'll have that small there, and big U is given by 3 halves, and then you have y over sigma minus 1 half quantity of y over sigma to the cube. So we're going to utilize that in finding for our du over dy. Now the next thing that we are going to do is to re-express this into u, that's small, is everything will just be multiplied by big U. So I'm just going to copy that y over sigma minus 1 half of quantity y over sigma to the cube. I will multiply U here. I don't know how will I do the distinction, but I'll just exaggerate. Okay, that's a big U over there. Now, once we get this U, basically, again and again, as I was saying, we have to solve for du over dy. Now, this is looking great since we have u here, the small u. So, what we are going to do next is to simply apply d over dy both sides. So, when I do that, I will have it like this one. I'll apply d over dy. So, that means if I apply that to the left, the same case happens with the right. Okay, so this is just another exercise of some basic differentiation laws. Now, when I apply du over dy on my left hand side, that is looking great because that's actually what I wanted to find. But you have to take note that on the right hand side, you are seeing here a product. So that means to say that you are going to employ, if you remember in our discussion, the product rule. Now, product rule, the mnemonic that we learned is we have it's fi, first derivative of the second plus the second derivative of the first. So we're going to do that here. So basically, I'm just going to write this one. First means I will copy everything. By the way, when we talk of first, I'm hoping it's clear to you that we are referring to this bracket quantity over there. So I'm just going to copy everything. So I have 3 halves y over sigma minus 1 half of the quantity y over sigma to the cube. That's my first. And then secondly is I will multiply it by the derivative with respect to y of the second term, which is u. Okay, I'm gonna emphasize u there. Okay, that's u. So we are done with first derivative of the second. Now, I know this is not very ideal, but I'm going to continue with my solution downward after the plus. So I'm gonna copy second, and guess what? The second, of course, is this term over here, this u, because that's your second function. So I'm gonna copy the second one is u. Okay, for emphasis, that's u multiplied by the derivative with respect to y of the first, which happens to be, in this case, 3 halves y over sigma minus the 1 half of quantity y over sigma to the cube. So basically, that's it. That's what you are going to do in the problem. However, I noticed something odd here. Okay, yeah, there's no problem. I thought there was a problem with the grouping symbol. Anyway, on the left-hand side, we have du over dy, and again, that is the small u. And what happens here, if we do some quick inspection, take note that q in this problem here, as you can see, I'm just gonna zoom in the problem and its illustration over here. Now that u is actually a constant. That means to say that's the velocity of your fluid on the topmost region. So with respect to how it changes, by the way, your height, just gonna emphasize again, your height is measured from the bottom to top, towards the top. So that's your height. Now, how does that u, big U, we're talking about this u here, how does that big U changes with respect to y is basically that does not change. So in a sense, your u there is a constant. Now take note that when you try to take the derivative with respect to a constant, we learned that from our review in calculus that will just be 0. So when you do that, this is actually very great news and very pleasing to the eyes. And it's like, yes, because everything that you are seeing here, the one that I'm highlighting, will just be zero because that is multiplied to zero. So I'm not gonna think about that anymore. I'm only gonna think about the second term that is left, which in this case is just this term here. So I am left with the big U multiplied by the derivative with respect to y. So I'm just gonna go over extra details here just to, like an exercise of what we've learned from our class. So I'm gonna have the derivative with respect to y distributed according to the theorem. We can do that 3 halves of y over sigma. So you just review the theorem. And then I'm gonna subtract d over dy of y over sigma to the cube. Now take note that there are some things that we can still simplify about it. So remember the theorem which says something that we can do about, by the way, just for emphasis, you have to remember that everything here is multiplied with respect or multiplied with u. So do not forget to have that bracket over there so that you can appropriately do the operation of operation. Okay. So I'm just gonna have multiply by everything here, and take note that this with respect to, this is just a very detailed solution, but just to exercise what you've learned and what you also reviewed in our class. So I could just take out that constant here, and with respect to y, sigma is also a constant. So what I am left is basically the derivative with respect to y of y. And that is quite a beauty. And if you do it over here, take note that how do we do that? That's basically in our discussion, we take the derivative of some x to the n, right? So if you remember, what we will do in that case is that is nx, n minus 1. So when we apply that in this case, we have 3, that's just the power, and then we copy the y minus sigma, and then 3 minus 2 is just, 3 minus 1 is just 2, and then take note that we need to perform chain rule here. So after that one, we still take the derivative with respect to y of what is left, which is y over sigma. So katunan na akong giingon nga ang sulod na lang dayon. So basically, you're doing chain rule. Okay, so let me just zoom out a little bit so that you'll see the process. So we're nearing our desired value, which is just du over dy. So again, I have the big U multiplied by everything that I'm getting here. So basically, a close inspection of the quantity here will reveal that this is just 1. So that is leaving you behind with 3 over 2 sigma. Now, how about this? So I'm gonna continue that I have 3 multiplied by y over sigma. That is squared. By the way, that's not 8. It looks like 8, but it's not 8. And when you try to take the derivative with respect to y, the same thing happen. You take out the constant and only take the derivative of what is left, which is y. And okay, this is something that we have already seen, and it's quite easy to understand that is just 1. Okay. But I failed to wait. That's 1. Okay, right. So when we have that one, what we're seeing here is a simplified version of what we want. That is just the du over dy is just equal to big U, and then do not forget the grouping symbol, and you have 3 over 2 sigma minus 3 quantity y over sigma, and that is squared. And when you try to multiply these two terms over here with this one, so I'm just gonna put the sigma over here, and yeah, that is just 1. So basically, this is your du over dy, or the velocity gradient. So we have solved for this one, as you can see there. And the thing that we are going to find again is just the tau. So your tau is just mu du over dy. So we don't have any problem with du over dy for now. But your mu, how do we get the mu? Of course, from the kinematic viscosity, we could get the mu, and we have actually solved that one here. Just find some good colors. Okay, so that's your mu, right? So I'm gonna write that here. So my mu is just that's like the kinematic viscosity 4 times 10 to the negative 4 meters per second multiplied by the density of the fluid, and everything will just be multiplied by du over dy, the one that we are seeing right over here. Okay. Now, another quantity arises that we are not quite sure what is the value for, and that is the density of the fluid, because that's not directly given in the problem. Okay, but upon inspection above, you're also seeing that from the specific gravity which is given in the problem, we could actually get the density of your fluid just by manipulation of the equation. So I'm just gonna substitute here again that the density will just be, so this is looking quite a little bit tedious, meters per second. The density of the fluid will just be 0.92 multiplied by the density of water, which is very easy to remember, and du over dy. Okay, I could actually continue with that one. Now, I'm just gonna copy this one. This is my tau, and do it on the bottom part because it's looking crowded. Copy, and let's do it on another page. Paste. So this is basically our tau. Now, if you try to substitute the values and try to calculate, that is just times 10 to the negative 4 meters per second, and then 0.92, and the density of water for it's very easy to remember, that's 100 kilograms per, 1,000 kilograms per cubic meters, and then your du over dy. So I'm just gonna write here u, okay, not that one, u multiplied by 3 over 2 sigma minus 3 over sigma multiplied by y over sigma squared. So that's your du over dy. Now, what I would emphasize at this stage is to realize, class, that this is actually telling us that we need to evaluate whatever your expression for velocity gradient at y is equal to 0. Why that is so? Because take note, the problem is saying here that you need to determine the magnitude and direction of the shearing stress developed on the plate. And it also says that express, okay, your answers in terms of u, and that is basically what we are doing. Now, the most significant thing that I would like to emphasize is developed on the plate. So, where is the plate? The plate is actually here. This is your plate. Oh, it's moving. This one here is your plate. That's your plate. And what is the value of the height y? That is 0. Therefore, on our velocity gradient, we need to evaluate it at y is equal to 0. Now, when that is the case, that's actually simplifying what we are seeing, because if you substitute this into 0, and basically the second term will just be 0, evaluate at y is equal to 0. So what is left of this expression is the one that I am highlighting, just this part. Okay? So when you get your calculator, you could actually get that whole number there will reduce to 0.368, and the units will be kilogram over meter squared multiplied by seconds, because that is what is required in the problem. The units, that's the kind of units that the problem is looking for. And you multiply it basically by the velocity gradient, which is evaluated at y is equal to 0. And clearly that is just 3u, that's a big U, over 2 sigma. So that is your developed shearing stress. So this is the shearing stress developed on the plate. So this is the shearing stress developed on the plate. Okay, so this is how you solve that problem. So it's basically just trying to make sense of the given, especially on some quantities and how you can manipulate them, and then you perform some basic calculus, and then after that you go back to the problem again, understand where should you evaluate the height y, which in this case is on the plate, so you evaluate it at y is equal to 0, and after doing that you get this surface tension, sorry, you get this this is your shearing stress developed on the plate.